to Starry Cosmos. Imagine a darkness so profound it stretches beyond anything you've ever conceived. A vastness where distances aren't measured in miles or light years, but in the whispers of gravitational influence. What if our galaxy, this swirling island of stars we call the Milky Way, wasn't truly alone? For billions of years, astronomers have charted its movements, observed its interactions with neighboring clusters. But recently, a new understanding has emerged, revealing something far grander. A network, a web of connections binding countless galaxies together. It's a realization that forces us to reconsider the very nature of space itself. Tonight, we'll journey into Laniakea, a colossal cosmic neighborhood containing 100,000 galaxies, and uncover the surprising force that shapes their movements. So dim your lights, settle in, get yourself comfortable, let your breathing slow, and let us begin. If these quiet journeys help you drift off, take a slow breath and subscribe to Starry Cosmos so the next one finds you when you need it. The darkness here is profound. A velvet curtain stitched with an impossible number of points of light. It's easy to feel adrift within it, to lose oneself in the sheer scale of what exists beyond our immediate perception. And yet, that feeling of being small, of being connected, is precisely what draws us to explore these immense spaces, to understand the forces that shape them. We begin by considering not just the appearance of the universe, but its underlying structure, a structure defined fundamentally by gravity. It's an unseen force, certainly one we can't directly perceive with our senses. Yet it dictates the movements of galaxies, the orbits of planets, and ultimately, the very fate of stars. Think for a moment about galactic clusters, behemoths formed from the gravitational attraction of hundreds, sometimes thousands, of galaxies bound together. They are not simply collections of stars drifting randomly. They are held in place, shaped by this mutual gravitational embrace. Within these clusters, individual galaxies themselves are swirling, rotating, and colliding, their trajectories dictated by the collective weight of everything around them. These aren't isolated islands in a sea of emptiness, but interconnected parts of something far grander. And it's within that grandness that we find one particular cluster, now known as Laniakea Hawaiian for immense ocean. Its discovery wasn't accidental. It arose from meticulous observation and the application of mathematical analysis. Scientists began by mapping the velocities of galaxies within a large cluster, the Shapley supercluster, a structure already recognized as encompassing numerous clusters themselves. They weren't simply measuring how fast each galaxy was moving in its own direction. They were tracking their peculiar motions, those deviations from a straight line that indicated they were being pulled on by something beyond their immediate neighborhood. These peculiar velocities told a story of gravitational influence, pointing towards the presence of an unseen mass large enough to distort space itself. Imagine a marble rolling across a blanket. If you place a heavy weight in the center, the marble will curve towards it, right? Galaxies behave similarly. They are caught within the embrace of something far more powerful, something that warps the very fabric of space-time. The process of charting these peculiar velocities led to the identification of a central gravitational attractor, a region so dense with galaxies and dark matter that it dictated the orbital motion of all those surrounding it. It wasn't just the most massive galaxy within the cluster, but rather the entire structure exerting its gravitational dominance. Now, let's consider how we actually know about this influence from such vast distances. The light itself carries information. The color and intensity of that light reveal the temperature, composition, and motion of the object emitting it. But as light travels across immense cosmic distances, it doesn't travel in a straight line, it bends. This bending is caused by gravity, a phenomenon predicted by Albert Einstein's theory of general relativity. This effect is called gravitational lensing. Think about a magnifying glass. It focuses light to create an image. Similarly, massive objects like galaxy clusters warp the space around them, causing light from more distant galaxies behind them to bend and distort as it passes by. The distortion can appear as multiple images of the same background galaxy, an arc surrounding the lensing object, or even a ring-like structure known as an Einstein ring. These aren't flaws in our instruments. They are direct consequences of gravity's influence on space-time itself. By observing these distortions, the way light is bent and magnified, astronomers can infer the mass distribution of the foreground galaxy cluster, even if we can't directly see it. It's like feeling the presence of a giant without being able to touch it, understanding its power through the ripples it creates in the universe. The brighter the distortion, the greater the mass warping spacetime. It's a powerful tool for mapping the unseen components of the cosmos. However, despite these incredible methods, gravitational lensing and the meticulous tracking of galactic velocities, observing distant galaxies poses significant challenges. Light travels at a finite speed, and that speed is simply too slow to allow us to witness events as they truly happen. When we look at a galaxy billions of light years away, we are seeing it as it was billions of years ago. The light started its journey towards us long before our own solar system even existed. The further we look into the universe, the further back in time we see. This is crucial to understand. Every single observation you've ever encountered that described a distant galaxy or a primordial star is inherently colored by this temporal distance. Think about it. The light reaching your eyes from the Andromeda galaxy today began its journey approximately 5 million years ago. That means we are seeing Andromeda as it was 5 million years ago, not as it is today. It's like trying to photograph a race without being able to record the video. You can only capture fleeting moments in time, and your understanding of what happened is inevitably incomplete. Furthermore, the expansion of the universe complicates matters even further. As space itself stretches, the light emitted by distant galaxies gets stretched along with it, a phenomenon known as redshift. The greater the distance, the more significant the redshift, effectively shifting the light towards longer wavelengths, towards the red end of the spectrum. This isn't simply a change in color. It also means that the energy of the light decreases, making it fainter and harder to detect. The most distant galaxies are therefore incredibly faint, requiring extremely sensitive telescopes and long exposure times to observe. It's like trying to hear a whisper from across an enormous canyon. The sound gets lost in the echoes and distortions before you can even perceive it. So when we speak of Laniakea, of this immense cosmic structure spanning 500 million light years, we are drawing together these threads. The fundamental force of gravity shaping galactic clusters, the visual clues revealed through gravitational lensing, and the inherent challenges of observing galaxies at such extraordinary distances. It's a testament to human ingenuity, our ability to detect faint signals across vast stretches of space and time, and ultimately to comprehend our place within this breathtakingly intricate and utterly humbling universe. The journey to unravel the secrets of Laniakea is still ongoing, each new observation building upon previous discoveries, refining our understanding of the cosmos and reminding us that we are inextricably linked to everything around us through the unseen web of gravity. And it all begins with a simple question. How does the motion of one galaxy reveal the presence and influence of countless others scattered across 500 million light years? The universe, as you've come to understand it, perhaps through countless journeys across its silent expanse, isn't a collection of isolated islands adrift in an endless void. It is something far more intricate, far more interwoven, a gigantic, shimmering web held together by the invisible threads of gravity. And if you consider the scale at which this web operates, stretching out for 500 million light years and encompassing 100,000 galaxies, it becomes clear that we're not merely observing a structure, we're inhabiting one, a sprawling cosmic home defined by the way galaxies cluster together, move, and ultimately relate to each other. It is an architecture crafted by forces so vast, so ancient, that their full implications are still unfolding before our eyes. And it all begins with a simple question. How does the motion of one galaxy reveal the presence and influence of countless others scattered across 500 million light years? For centuries, astronomers had largely accepted a model of the universe based on what was then considered common sense, that galaxies existed within clusters, bound together by their mutual gravitational attraction. The prevailing theory, championed by scientists like Harlow Shapley in the 1920s, posited the existence of giant islands of light, enormous collections of galaxies held together by gravity, with our own Milky Way residing comfortably within one of these sprawling formations. These models envisioned clusters as relatively static structures, with galaxies orbiting a central point, a kind of galactic anchor, much like planets revolving around a star. The challenge, however, lay in accurately predicting and observing the motions within those clusters. Measurements were often imprecise, relying on limited observational data and assumptions about the distribution of mass, particularly dark matter, which at that time was largely theoretical. Many clusters appeared to be moving faster than expected based solely on the visible matter they contained, leading to a kind of observational dissonance. The standard model wasn't quite adding up when confronted with the reality of galactic dynamics. It's within this context that the work of Vera Rubin began to emerge as something truly revolutionary. Born in Kenai Island, New York, in 1928, and earning her PhD from Columbia University in 1951, Rubin initially focused on stellar atmospheres, diligently studying the spectra of stars to understand their composition and temperature. But it was her growing interest in the motions of galaxies that would ultimately transform our understanding of the universe. She joined Princeton University's Department of Astrophysics in 1968, inheriting a project investigating the rotation curves of spiral galaxies, a puzzle that had been perplexing astronomers for nearly half a century. A rotation curve, as you might visualize it, plots the orbital speeds of stars and gas clouds within a galaxy against their distance from the galactic center. Based on Newtonian physics, one would expect to see a consistent relationship. As you move further away from the center, where most of the visible mass is concentrated, the orbital speed should decrease, mirroring the way planets orbit the Sun. The closer you are to the Sun, the faster you're moving. As you move farther out, the same amount of sunlight takes longer to reach you, so your velocity slows down. This is because gravity's influence diminishes with distance. It's a simple and elegant principle, deeply ingrained in our understanding of orbital mechanics. However, when Rubin and her team began meticulously measuring the velocities of galaxies across vast distances, using the Palomar Observatory's 48-inch telescope, they discovered something utterly unexpected. They found that the rotation curves didn't follow this predicted decline. Instead, they observed a remarkable consistency. The orbital speeds remained constant, or even increased, as they moved further out from the galactic center. It was as if the stars and gas clouds at the outer edges of galaxies were orbiting just as fast as those closer in, defying all expectations based on the visible matter within each galaxy alone. This observation led Rubin to introduce the concept of peculiar velocities. These peculiar velocities represent motions that are independent of the gravitational pull of the galaxy's own rotation. They are deviations from the orbital motion you would expect if only the gravity of the galaxy itself were acting upon it. Imagine a leaf floating down a river. The current, representing the overall galactic rotation, will influence its movement. But the leaf might also be tossed sideways by turbulence. That's akin to a peculiar velocity. These peculiar velocities are caused by gravitational influences from other galaxies and clusters within the cosmic web. Each galaxy is not just orbiting around its own center. It's being tugged and pulled by the combined gravity of countless neighboring galaxies, creating a complex dance across immense distances. Prior to Rubin's work, many attempts had been made to explain these anomalous rotation curves. Some theories proposed that vast quantities of unseen mass, dark matter, were distributed throughout galaxies, extending far beyond the visible disk. This dark matter would exert gravitational influence on the stars and gas clouds, maintaining their high orbital speeds at large distances. However, these models often struggled to accurately predict the observed patterns of peculiar velocities. They tended to oversimplify the complex interactions between galaxies, often assuming a homogeneous distribution of dark matter, rather than acknowledging its clumpy, irregular nature. Other approaches attempted to incorporate concepts like tired light, the idea that light loses energy as it travels through space. But these ideas ultimately lacked solid evidence and were eventually discarded. Rubin's crucial contribution wasn't simply the discovery of anomalous rotation curves. It was the meticulous and systematic way she gathered and analyzed the data, coupled with her unwavering belief in the accuracy of her measurements. She spent years painstakingly observing hundreds of galaxies, refining her techniques and challenging conventional assumptions. Her team used a technique called spectroscopic redshift to determine distances and velocities, analyzing the shift in light wavelengths caused by the expansion of the universe. The greater the redshift, the faster the galaxy is moving away from us, and the further away it is. It was a process of painstaking refinement, built on careful observation and rigorous analysis, that ultimately laid the foundation for understanding the remarkable structure of the Laniakea supercluster. The implications of Rubin's findings were profound. They provided compelling evidence that galaxies weren't simply isolated islands of light, but were instead embedded within a vast, interconnected network of gravitational influence, a web meticulously woven by the dynamics of dark matter and the motions of countless other galaxies. Furthermore, her work shifted the focus from describing individual galaxies to understanding their relationships within larger cosmic structures. It sparked a revolution in cosmology, prompting scientists to reevaluate our fundamental assumptions about the universe's architecture and its evolution. The Laniakea supercluster, that majestic tapestry of 100,000 galaxies stretching for 500 million light years, wasn't merely an observation. It was a consequence of Rubin's extraordinary dedication, a testament to the power of persistent questioning and disciplined scientific inquiry. And as you continue your journey through this web, remember that every point of light you observe is connected, intertwined, part of a larger dance orchestrated by gravity across the vastness of space and time. Let's consider for a moment what it means to stand at a watershed, a boundary where one stream of water flows into another, shaping the land with its passage. Now imagine that concept applied not to water, but to gravity itself. A gravitational watershed isn't simply a line on a map. It represents a critical transition point within the cosmos, a place where the direction and strength of gravitational forces fundamentally shift, determining which galaxies will be drawn towards a particular center and which will drift away. It's a zone defined not by flow, but by influence, a region where the subtle tugs exerted by nearby mass become overwhelmingly dominant, dictating the fates of countless celestial bodies for billions of years to come. The term itself was coined by Vera Rubin, an extraordinary astrophysicist whose dedication to unraveling the mysteries of our universe extended over decades. And her research group at the Cavendish Laboratory in Cambridge, they noticed a peculiar pattern, a subtle but persistent connection between galaxies that appeared to be moving towards each other, even when there wasn't enough visible matter, just dark matter, to account for such interactions. Rubin and her team realized they were observing something far more profound than simple attraction. They were witnessing the effects of gravity acting across vast distances, shaping the large-scale structure of the cosmos in a way that demanded a new framework for understanding. It was a revelation born from meticulous observation, rigorous calculation, and an unwavering commitment to seeing connections where others hadn't yet looked. To understand this shift, let's consider how galaxies themselves transition between different gravitational poles. Imagine a galaxy like our own Milky Way, a swirling collection of hundreds of billions of stars, gas clouds, and dark matter, all held together by the relentless force of gravity. Now picture that galaxy not as an isolated entity, but as one member within a much larger, interconnected network. Galaxies aren't simply floating randomly in space. They're constantly interacting with their neighbors, pulled towards them by gravitational attraction. The closer you are to a massive object, like a giant elliptical galaxy or a dense cluster of galaxies, the stronger the pull becomes. As you move further away, the gravitational influence diminishes and you begin to drift outwards. This isn't a sudden snap. It's a gradual process driven by subtle shifts in the balance between attraction and repulsion, influenced by factors like expansion of space itself and the varying density of matter along the lines of sight. Think of it like a river flowing into a widening basin. Initially, the current is strong, pulling you towards the center. But as the basin expands, the flow becomes gentler, eventually leading you to spill out into a broader expanse. Galaxies aren't static objects. They are constantly moving, accelerating, and changing their trajectories in response to the gravitational landscape around them. Some galaxies will be caught in slow spirals, drawn ever closer to a central hub, while others will embark on more erratic journeys, propelled outwards by the expansive force of the universe. The key to identifying these watersheds lies in a sophisticated mathematical framework developed primarily by Matthew Walker and his collaborators at Johns Hopkins University. They utilized something called the flow algorithm, a method based on calculating the Hubble flow, the overall expansion rate of the universe, along different lines of sight to galaxies across vast distances. Essentially, they tracked how the velocities of galaxies appeared to change as you moved through space, accounting for the distortions caused by the curvature of space-time due to gravity. This isn't a simple matter of measuring speeds. It's about analyzing the apparent changes in velocity as observed from Earth. Because light takes time to travel, when we observe a distant galaxy, we are seeing it as it was millions or even billions of years ago, at a different stage in its evolution and within a different gravitational environment. The flow algorithm works by constructing a three-dimensional map of these apparent velocities, essentially tracing the paths galaxies appear to be taking through space, and then identifying where these paths abruptly change direction or accelerate dramatically. These abrupt changes aren't random. They represent points where the gravitational influence from nearby structures becomes dominant, pulling galaxies along a new axis. The algorithm is remarkably sensitive, allowing scientists to pinpoint these transition zones with extraordinary precision. It's important to remember that this isn't about detecting individual galaxies. It's about mapping the influence of gravity, the cumulative effect of countless smaller forces acting in concert. The watershed isn't a single galaxy. It's a region defined by the collective behavior of many. Within this framework, a remarkable discovery emerged. Our own Milky Way resides within what Rubin and her team termed the Laniakea supercluster. This name, meaning immense ocean in Hawaiian, perfectly captures the scale and grandeur of this cosmic structure. Laniakea isn't just a cluster of galaxies. It's an enormous void, spanning approximately 530 million light-years across, encompassing over 90,000 galaxies, including our own. The boundaries of Laniakea are defined by the flow algorithm, identifying the region where the Milky Way's motion is dominated by the gravitational pull of the Great Attractor, a massive concentration of unseen matter located roughly 400 million light-years away. It's within this immense web that most galaxies, including our own, are currently moving, pulled towards the Great Attractor, destined to eventually become part of its swirling embrace. But critically, Laniakea isn't a static entity. It's constantly evolving as galaxies migrate and merge, influenced by the gravitational dance occurring across this vast expanse. Galaxies on the outer edges of Laniakea are moving away from the Great Attractor, accelerating into the ever-expanding universe, while those closer in are drawn deeper into its gravitational well. The identification of Laniakea as a watershed has profound implications for our understanding of the large-scale structure of the cosmos. It demonstrates that gravity doesn't act in isolation. It's part of a complex, interconnected web, shaping the evolution of galaxies and influencing the very fabric of space-time. It highlights the importance of considering not just individual objects, but their relationships within a broader context, a concept central to both astrophysics and philosophy. The discovery also underscores the immense distances involved. A 500 million light-year expanse is a scale that truly defies human comprehension. Yet it represents a profoundly interconnected network of galaxies bound together by the invisible threads of gravity. Further investigations using data from telescopes like the Hubble Space Telescope and the James Webb Space Telescope are constantly refining our understanding of Laniakea's boundaries and dynamics. These observations reveal subtle variations in galaxy velocities and positions, providing valuable insights into the processes that govern this immense gravitational structure. The ongoing study of Laniakea is a testament to human curiosity and our relentless drive to unravel the mysteries of the universe. A continuing exploration of the profound connections that link us all across space and time. Consider for a moment, as you reflect on this vastness, the sheer improbability of your own existence within this network, an improbable outcome arising from billions of years of gravitational interactions, cosmic evolution, and the fundamental laws governing the universe. It's humbling, isn't it? And yet, here we are, contemplating it all. The universe doesn't announce its grand designs with fanfare. It reveals them subtly through the quiet dance of gravity itself. And within that dance, a particularly striking pattern emerged. A sprawling network traced across billions of light years, revealing our place within what we now call Laniakea. It's a name given by Dr. Alan Peacock and his team, reflecting its Hawaiian origin, heavenly waters, and capturing the sense of being carried along, adrift in currents of space. The story of Laniakea isn't just about finding it. It's fundamentally about how we learned to see it, a testament to patience, precision, and the remarkable power of observation. And much of that observation began with the Hubble Space Telescope, a truly extraordinary instrument that has gifted us an unprecedented view into the heart of our cosmic neighborhood. For years, astronomers had recognized that galaxies weren't randomly scattered across space. They tended to cluster together, forming groups and superclusters, vast, gravitationally bound structures reflecting the imprints of the universe's early expansion. But understanding the relationships between these distant systems remained elusive, obscured by the sheer distances involved. Then came the realization that some galaxies appeared to be moving towards others within these clusters, not just orbiting a central point, but being actively drawn together in a way that suggested a larger, overarching gravitational influence. It was a puzzle demanding a new approach, one that moved beyond simply cataloging individual galaxies and towards mapping the very streams of motion connecting them. The breakthrough came with Hubble's ability to measure the velocities of these galaxies with extraordinary accuracy. Velocity is, quite simply, how fast something is moving. But in astronomy, it's not about cars or airplanes. It's about the rate at which an object shifts its position against the backdrop of the distant universe. Astronomers use a phenomenon called redshift and blueshift to determine these velocities. Light waves naturally stretch as they travel across vast distances. This stretching is known as redshift, causing the light from receding objects to shift towards the red end of the spectrum. Conversely, if an object is moving towards us, its light compresses, shifting towards the blue end blueshift. Hubble's sensitive instruments could precisely measure these shifts in wavelength, allowing scientists to calculate how quickly each galaxy was moving relative to our own location within Laniakea. The data wasn't simply collected. It was meticulously processed by teams of researchers around the world. Each galaxy observed provided a valuable piece of the puzzle, and the sheer volume of observations accumulated over decades, spanning countless hours of telescope time, eventually amounted to an incredibly detailed map of galactic velocities. Initially, the raw data presented a chaotic picture. Individual galaxies exhibiting different speeds and directions. But as more measurements were taken, patterns began to emerge. Certain groups of galaxies consistently moved in similar directions, suggesting they were all influenced by a dominant gravitational force. It was like tracing ripples in a pond. Each ripple reflects the disturbance created by a stone dropped into the water. The method used to build this map relied on what is known as the virial theorem. This theorem essentially states that in a gravitationally bound system, the average kinetic energy, the energy of motion of the members, is equal to half the potential energy, the energy stored due to gravity. Applying this principle to Laniakea allowed astronomers to estimate the total gravitational pull exerted by all the galaxies within the structure, and from there predict the overall movement. Crucially, it wasn't just about measuring velocities. It was about understanding the relationships between those velocities, how they interconnected to reveal a larger, coherent pattern. The process involved complex simulations and statistical analysis, allowing researchers to identify watersheds, points in space where the gravitational influence of Laniakea dominated over that of neighboring clusters. These watersheds acted as boundaries, defining the regions within which galaxies were primarily pulled towards Laniakea. Imagine a river flowing through a valley. The watershed defines the boundary between the areas drained by the river and those drained by adjacent streams. Similarly, in the vast expanse of space, Laniakea's gravitational pull dictated which galaxies would be drawn into its embrace. The formation of Laniakea itself wasn't an instantaneous event, but a gradual process unfolding over billions of years. It began with the initial conditions established during the Big Bang. Tiny fluctuations in density that seeded the formation of the first structures in the universe. These fluctuations grew under the relentless influence of gravity, eventually leading to the collapse of matter into the large-scale structures we observe today. Galaxies, groups, clusters, and ultimately Laniakea. The expansion of the universe played a critical role. As space stretched, gravitational forces became increasingly dominant, pulling matter together to form larger and larger structures. The observations from Hubble didn't simply reveal an existing structure. they provided evidence for its ongoing formation. Galaxies are not static entities. They continue to interact with each other through gravity, merging and colliding to reshape the structure of Laniakea over time. The movement of galaxies within Laniakea isn't a fixed trajectory, but a dynamic process. Galaxies constantly accelerate as they move through the gravitational field, gaining speed as they get closer to regions of higher density. Furthermore, the researchers weren't just looking at redshift. They considered other factors like distance, because distance and redshift are intimately linked. Using Hubble's precise measurements of distance, coupled with the velocities derived from redshift, allowed for a more robust determination of recession velocity. This multifaceted approach provided a much clearer picture than relying on either measurement alone. The team utilized sophisticated computer models to simulate these gravitational interactions, allowing them to test different scenarios and refine their understanding of Laniakea's evolution. These simulations took into account not only the gravity of the galaxies themselves, but also the influence of dark matter, a mysterious substance that makes up about 85% of the universe's total mass and exerts a significant gravitational pull, even though we can't directly observe it. Dark matter's presence profoundly shaped the structure of Laniakea, acting as a scaffolding upon which galaxies formed and clustered. The resulting map of Laniakea isn't just a static snapshot in time. It's a dynamic representation of a system that is constantly evolving. As Hubble continues to observe galaxies within this region, scientists will be able to further refine the map and gain an even deeper understanding of its formation and evolution. It's a humbling reminder that we are part of something vast and intricate, a cosmic structure shaped by forces beyond our full comprehension. The scale of Laniakea is difficult to grasp, roughly 500 million light years in diameter, encompassing over 100,000 galaxies. To put that into perspective, a light year is the distance light travels in 1 year approximately 6 trillion miles. So, we're talking about a region of space so immense that it would take light 500 million years to traverse its entire extent. Within this expanse, our own Milky Way galaxy resides, along with countless other galaxies, all bound together by the gravitational pull of Laniakea. It's a truly staggering realization that our galaxy isn't an isolated island in space, but one member of a sprawling, interconnected cosmic web. And as you consider this map, this gravity web, it prompts questions about the ultimate fate of the universe, whether it will continue to expand indefinitely or eventually collapse back upon itself in a process known as the Big Crunch. The answer, of course, remains uncertain, but Laniakea serves as a powerful illustration of the ongoing interplay between gravity and expansion, a fundamental force that shapes the very fabric of reality. It invites us to contemplate our place within this grand cosmic architecture, urging us to continue exploring, observing, and striving to unravel the mysteries of the universe. The light of distant galaxies has carried across unimaginable distances to reach us, a testament to the universe's patient unfolding, revealing structures that stretch back billions of years. We find ourselves now considering the implications of this vast network, painted with the threads of gravity itself. Let's turn our attention to an element within this web, one intimately familiar, yet strangely distant: our own Milky Way galaxy. It is a place we inhabit, a home woven from stardust and swirling gas. But understanding its relationship to Laniakea offers us a crucial perspective on just how connected everything truly is. Consider for a moment the scale of things. 500 million light years is an almost unfathomable distance. Each light year represents the vast expanse of light traveling at 30,000 miles per second, a journey that would take nearly 600,000 years to complete. Yet within this immense reach, galaxies gather and orbit, bound together by the invisible force of gravity. And within this grand network, our Milky Way occupies a specific location, one defined not just by its physical size, which is considerable, containing perhaps 100 to 200 billion stars, but by its movement its velocity, and ultimately its relationship to all the other galaxies around it. We can think of Laniakea as a cosmic ocean, and the Milky Way, along with dozens of other similarly sized groups of galaxies, as islands within that ocean. These islands aren't isolated. They interact, merge, and even tear each other apart over immense timescales. But their movements are all dictated by the overarching gravitational flow emanating from a single point, the Great Attractor. Now, pinpointing the Milky Way's location within Laniakea isn't as straightforward as simply measuring its distance from a particular landmark. Because we are inside this system, observing it directly is incredibly challenging, and that presents unique difficulties in determining exactly where we are. The primary method used to determine our position relies on the motions of other galaxies. Astronomers carefully track the velocities of hundreds of these distant objects, primarily spiral galaxies like Andromeda and Triangulum, as they traverse the space around us. These aren't just simple speed measurements. Scientists analyze their redshifts, which is a phenomenon caused by the expansion of the universe stretching light waves, effectively shifting them towards the red end of the spectrum. The greater the redshift, the faster an object appears to be receding from us. By combining these velocity measurements with the observed positions of the galaxies, researchers can create what are known as flow maps, visual representations showing how the cosmos is flowing in different directions. These flow maps reveal a fascinating pattern. Most galaxies are moving away from us, confirming Hubble's law, which states that the speed at which a galaxy recedes from us is proportional to its distance. However, our Milky Way isn't simply drifting outwards with all the other galaxies. It's caught in a swirling current. The flow map reveals that we're being pulled towards the northeast, an area approximately 500 million light years away. This pull isn't the result of any single galaxy exerting dominance. Instead, it's a collective effect caused by the combined gravitational influence of dozens of galaxies concentrated within the Laniakea supercluster. The Great Attractor, located roughly 2 billion light years away, is the primary driver of this flow. It represents an immense concentration of mass, including dark matter, which makes up about 85% of all matter in the universe. That's warping space-time and effectively dragging us along with it. The Milky Way's rotation isn't a simple circular motion. Instead, our galaxy is rotating around this gravitational center at a remarkable speed, around 200 kilometers per second. This velocity is largely determined by Laniakea's gravitational pull, influencing the orbital speeds of countless stars and gas clouds within our own galaxy. Imagine being on a giant merry-go-round, not just spinning, but also being gently nudged by an invisible force. That's essentially what's happening to the Milky Way. Now, let's consider the challenges inherent in observing our own galaxy from afar. It's akin to trying to map your surroundings while you're standing directly inside them. Our perspective is fundamentally biased. We're surrounded by stars, gas clouds, and dust, all of which obscure our view of the galactic core and create significant distortions in our observations. The interstellar medium itself absorbs and scatters light, making it incredibly difficult to see objects behind it. Furthermore, because we are embedded within this rotating system, measuring distances accurately is a complex undertaking. We rely on techniques like parallax, measuring the apparent shift in a star's position against the backdrop of distant galaxies. As the Earth orbits the Sun and standard candles, which are objects with known intrinsic brightness that allow us to estimate their distance based on how bright they appear to us. However, applying these methods within the Milky Way is more challenging due to the intervening dust and gas, requiring sophisticated corrections and models to account for these effects. Scientists utilize a technique called kinematic modeling to disentangle the complex motions of stars and gas clouds within the Milky Way by precisely measuring their velocities and positions. They can reconstruct the galaxy's rotation curve, a graph showing how velocity changes with distance from the galactic center. This rotational curve provides crucial information about the distribution of mass within the Milky Way, including the amount of dark matter that is thought to reside in a halo surrounding the visible disk. The observed shape of the Milky Way's rotation curve has been one of the most significant clues pointing towards the existence of dark matter. According to Newtonian physics, galaxies should rotate slower at larger distances from their centers if they contained only the mass we can directly observe. However, observations reveal that velocities remain relatively constant or even increase slightly with distance, indicating a substantial amount of unseen mass, dark matter, is contributing to the galaxy's gravitational pull. Even with all these sophisticated techniques, our understanding of the Milky Way's structure and dynamics is still evolving. New data from telescopes like Gaia, which is meticulously mapping the positions and motions of over 1 billion stars, are continuously refining our knowledge. As we gather more observations and develop increasingly powerful computational models, we'll continue to peel back the layers of complexity surrounding our galactic home. The Milky Way's position within Laniakea isn't merely an academic exercise. It highlights the profound interconnectedness of all things in the universe. It underscores the idea that galaxies aren't isolated entities, but are instead embedded within a vast, intricate network governed by gravity. By studying the motions of our own galaxy, we gain invaluable insights into the workings of this larger system and, ultimately, into the very fabric of the cosmos itself. It's a humbling reminder of our place in a universe that is both immensely grand and intimately connected, a realization that continues to inspire exploration, observation, and the relentless pursuit of knowledge about the mysteries that still lie hidden within the deep space around us. The journey to truly understand Laniakea, and therefore ourselves, is far from over. The vastness of Laniakea continues to unfold, a tapestry woven from the threads of gravity itself. We've traced its boundaries, mapped its influence, yet it remains profoundly humbling to consider the sheer number of worlds, of active galaxies, nestled within this single cosmic neighborhood. our awareness expands with each discovery, revealing not just distances, but intricate relationships, delicate balances maintained by forces we strive to comprehend fully. Let us now turn our attention to some of the more remarkable members of Laniakea, starting with structures that lie relatively close to our own Milky Way galaxy, and then venturing outwards into the grander scales of clustered galaxies. It is within these local gatherings where the most immediate gravitational interactions play out, offering invaluable insight into the dynamics governing this immense web. Consider first the Magellanic Clouds, those two distinct islands of stars visible in the southern sky, often mistaken for a single faint nebula. They are, in fact, dwarf galaxies, satellites orbiting our own Milky Way. The large Magellanic Cloud is considerably larger than its companion, the small Magellanic Cloud, and estimates suggest that it contains between 100 million and 200 million stars, a fraction of the population within the Milky Way, certainly, but still a galaxy in its own right, possessing its own spiral structure, though far more loosely defined and blurred by its proximity. The stars themselves are predominantly older, redder in color, reflecting the long lives these smaller galaxies have experienced since their formation. They've been subjected to the Milky Way's gravitational pull for billions of years, a constant dance of attraction and escape that has shaped their orbits and ultimately influenced their evolution. Scientists suspect that the Magellanic Clouds may eventually collide with the Milky Way, though this event is predicted to occur over several billion years from now. A slow, complex process involving tidal forces ripping apart stellar streams and transforming the shapes of both galaxies. The small Magellanic Cloud is particularly active, exhibiting bursts of star formation as it interacts with the disk of the Milky Way, feeding on gas and dust pulled in by gravitational attraction. It's a spectacular display of cosmic cannibalism, a testament to the dynamic nature of these stellar systems. Studying them offers invaluable clues about how galaxies form and evolve, particularly those smaller than our own, moving outward we encounter the Virgo cluster, a truly colossal aggregation of galaxies located approximately 61 million light-years away. It represents one of the closest galaxy clusters to Earth, providing astronomers with an exceptional opportunity to study galactic evolution in detail. The Virgo cluster is estimated to contain between 140 and 230 galaxies, ranging from large elliptical galaxies, some hundreds of billions of stars apiece, to smaller spiral and irregular galaxies. Many of these galaxies were once independent spirals like the Milky Way, having been drawn into the cluster's gravitational embrace over cosmic timescales. The cluster's overall mass is immense, dominated by dark matter, a mysterious substance that we can't directly observe, but whose gravitational effects are undeniable. This dark matter creates a deep potential well, acting as the primary driver of the cluster's dynamics. The galaxies within the Virgo cluster orbit around a common center of mass located at the cluster's core, a concentration of mass that is itself shrouded in darkness, yet exerting immense influence. The velocity dispersion, how fast the galaxies are moving relative to each other, is remarkably high within the Virgo cluster, indicating the powerful gravitational forces at play. Galaxies are flung around this central point at tremendous speeds, constantly colliding and interacting with their neighbors. The cluster isn't static. It's actively merging with smaller groups of galaxies, further increasing its size and complexity. These mergers trigger bursts of star formation as gas clouds collide and compress, ultimately leading to the birth of new generations of stars. The immense density of galaxies within the Virgo cluster also creates intense tidal forces, distortions in the shape of galaxies caused by the gravitational pull of nearby objects. These tidal effects are particularly evident in the tidal tails, long streams of stars and gas that have been ripped away from member galaxies, tracing the outlines of the cluster's gravitational influence. The gravitationally interactions within Laniakea aren't simply about attraction. They involve a delicate ballet of forces. Gravitational attraction pulling galaxies together, but also repulsive forces generated by the expansion of space itself. This tension between gravity and expansion shapes the very structure of the web, dictating how galaxies cluster and move relative to each other. The Milky Way, as we've established, is caught within this web, orbiting a point called the Laniakea supercluster, a region containing thousands of galaxies spread across a distance of approximately 530 million light years. As our galaxy moves through this vast space, it interacts with other members of Laniakea, experiencing periods of acceleration and deceleration depending on its trajectory. These interactions aren't isolated events. They contribute to the overall dynamics of the entire web. The velocities of galaxies within Laniakea are not random. They follow a characteristic distribution that reflects this interconnected gravitational landscape. Galaxies tend to move faster when they are closer to the cluster's center, and slower as they move outwards, a direct consequence of their position within the web's potential well. The Magellanic Clouds and the Virgo cluster offer tangible examples of how gravity shapes the universe at its most local level. But the true scale of Laniakea extends far beyond these immediate neighbors. It is a network, an intricate structure spanning billions of light years, connecting galaxies across vast cosmic distances. Studying these individual components, their formation histories, their interactions with each other, and their movement within the web allows us to build a more comprehensive understanding of this grand architecture. The observation of gravitational lensing, the bending of light around massive objects, provides further evidence for Laniakea's structure. Massive galaxies and clusters warp spacetime itself, causing the light from galaxies behind them to bend and distort, creating multiple images or arcs of the same distant object. This phenomenon not only confirms the presence of these concentrations of mass, but also allows us to measure their distances with unprecedented accuracy, a crucial tool for mapping the web's geometry. The ongoing research into Laniakea is not merely an exercise in cataloging galaxies. It's about uncovering fundamental principles governing the evolution and behavior of the universe itself. It forces us to confront questions about dark matter, dark energy, and the interplay between gravity expansion and structure formation. Every new observation, every refined calculation brings us closer to a more complete picture. A picture that recognizes the profound interconnectedness of all things in this vast expanse. And as we continue to explore these gravitational watersheds, we gain a deeper appreciation for our own place within the grand cosmic tapestry. The study of Laniakea is a reminder that we are not just observers of the universe. We are irrevocably part of it, bound together by the same fundamental forces that shape its evolution and structure. Consider for a moment the sheer scale of what we've been exploring. This vast archipelago of galaxies stitched together by the invisible threads of gravity. We've traced the boundaries of Laniakea, a region so immense it encompasses 100,000 celestial islands, each one a swirling repository of stars and gas, a testament to the universe's ongoing creative process. But within this colossal network, there exists an astonishing diversity, a breathtaking cosmic zoo where galaxies exhibit an array of shapes and behaviors that defy simple explanation. It's a place where the fundamental laws governing gravity and motion have sculpted structures of unimaginable beauty and complexity. And as you observe it now, you begin to grasp just how much we still have to learn about this remarkable, interconnected web. The first thing that strikes you when surveying Laniakea is the incredible variety of galactic morphologies. You encounter spiral galaxies like our own Milky Way, with their elegant pinwheel arms spiraling outwards from a central bulge. Structures built over billions of years through the relentless accretion of gas and dust, influenced by gravitational interactions with smaller satellite galaxies. These spirals aren't uniform. Some are tightly wound, almost perfectly symmetrical, while others exhibit more chaotic, fragmented patterns, reflecting the complex interplay of forces at play within their halos. Then there are the elliptical galaxies, appearing as smooth, featureless blobs, often found clustered together in the denser regions of Laniakea, the remnants, perhaps, of ancient galactic mergers, shaped by a violent past into something far more compact and ordered. Their bright cores suggest intense star formation events long since concluded, while their sparse populations indicate that much of their interstellar gas has been stripped away through interactions with neighboring galaxies. And then you find the irregulars, galaxies lacking any discernible symmetry, appearing as chaotic clouds of stars and dust, often found orbiting within larger spiral galaxies. These are frequently the most actively forming galaxies, fueled by bursts of star birth triggered by gravitational disturbances or collisions with other galaxies, a process that reshapes their structures in dramatic and unpredictable ways. Each galaxy type represents its own unique chapter in the story of cosmic evolution, presenting a range of processes, some gentle, some explosive, that have shaped the universe around us. Scientists suspect that within these varied forms lies the key to understanding how galaxies truly form, a process far more intricate than simply gravity pulling matter together. The shapes we observe are not arbitrary. They are intimately linked to the environmental factors acting upon each galaxy throughout its existence. Galaxies don't simply exist, they respond to their surroundings. Consider the concept of tidal forces, the gravitational pull exerted by a larger galaxy on a smaller one, distorting its shape and triggering star formation. A spiral galaxy, for instance, passing close to a massive elliptical galaxy, will experience significant tidal distortions, stretching and warping its arms as it's pulled into a stream of stars. Similarly, galaxies residing within dense clusters are subjected to constant gravitational harassment from their neighbors, leading to increased rates of collisions and mergers, events that fundamentally alter galactic shapes and drive star formation. The density of the surrounding dark matter halo also plays a crucial role. Galaxies embedded in denser halos tend to have higher rotation velocities and more extended stellar disks, while those residing in sparser environments exhibit slower rotation speeds and tighter, more compact structures. You can almost visualize dark matter as a giant, invisible hand, gently pushing or pulling on these galactic forms, shaping them over vast timescales. Furthermore, the distribution of hot gas within a galaxy's halo exerts a significant influence on its morphology. Galaxies rich in hot, X-ray emitting gas, a byproduct of active star formation, tend to have more extended disks and higher rotation velocities, while those with less gas tend to be more compact and elliptical. This interplay between dark matter, the distribution of hot gas, and the gravitational forces exerted by neighboring galaxies creates a complex feedback loop that determines the final shape of each galaxy. It's not just about gravity. It's about the entire galactic ecosystem working in concert. Theories surrounding galaxy formation offer many layers, interwoven with observation and speculation. The prevailing model suggests that small density fluctuations in the early universe, tiny variations in the distribution of matter, seeded the formation of gravitational wells. These wells acted as catalysts, drawing together increasing amounts of dark matter and gas, eventually leading to the collapse of vast clouds of material, the seeds from which galaxies sprang forth. However, this initial collapse wasn't always smooth or symmetrical. Simulations demonstrate that mergers, collisions between smaller galaxies, play a crucial role in boosting star formation rates, triggering intense bursts of activity that can reshape entire galaxies within relatively short periods. These mergers aren't just simple collisions. The gravitational forces involved create tidal tails, long streams of stars and gas flung outward during the interaction, dramatically altering the shapes of both merging galaxies. There are also theories about ram pressure stripping, whereby a galaxy moving through the hot intergalactic medium loses its gas more rapidly than it can replenish it via star formation. This causes the galaxy's disk to become thinner and more concentrated, eventually leading to an elliptical shape. And then there's the concept of dark matter halos, the vast, invisible structures thought to surround galaxies, providing the gravitational scaffolding for their formation and evolution. The precise nature of dark matter remains one of the greatest mysteries in modern cosmology, but its influence on galactic structure is undeniable. Furthermore, recent research highlights the importance of feedback processes. Energetic outflows from supernova and active galactic nuclei, supermassive black holes at the centers of galaxies, can inject vast amounts of energy back into the interstellar medium, suppressing star formation and regulating galaxy growth. These feedback mechanisms often create a dynamic tension between gas accretion, the influx of new material onto a galaxy, and star formation, the process of converting gas into stars. The balance between these two opposing forces determines whether a galaxy will continue to grow and evolve or eventually stall and become quiescent. The study of Laniakea, therefore, isn't just about mapping the distribution of galaxies. It's about unraveling the complex interplay of physical processes that govern their evolution, from the delicate balance between gravity and gas dynamics to the disruptive forces of mergers and feedback mechanisms. As you contemplate this sprawling cosmic zoo, you begin to realize that each galaxy represents a unique experiment in the universe's ongoing quest for complexity, an intricate dance of forces sculpted over billions of years. It's a humbling reminder of our place within this grand scheme, a tiny speck within a magnificent network, inextricably linked to every other component. The sheer scale presents endless questions, inviting deeper investigation and a continued refinement of our understanding of the cosmos. The immense reach of Laniakea continues to reveal itself as a testament to fundamental forces shaping our universe, its boundaries defined by the subtle yet powerful influence of gravity. We find ourselves now considering not simply where we are within this network, but how we arrived here, and what that arrival tells us about the very nature of space and time. The expansion of the universe is not a gentle stretching, as one might initially conceive, but an acceleration, a relentless pushing outwards driven by something we still don't fully comprehend. It's this accelerating expansion, often referred to as dark energy, that forms the core of our examination today, revealing itself through the graceful movements of galaxies within Laniakea, and prompting a profound reconsideration of how we understand the cosmos as a whole. Consider for a moment what it means for something to expand. A balloon inflated with air provides an intuitive image. Its surface area increases as more air is pumped, driven by the force of the expanding gas. But space itself isn't filled with gas, and the expansion of the universe doesn't work quite like a balloon. Instead, it's a property inherent to space-time itself, that fabric upon which all things exist being stretched. And while gravity, the attraction between objects with mass, would intuitively suggest a contraction towards denser regions, the observed reality is precisely the opposite. Galaxies aren't drawn together. They are propelled further apart with increasing speed. The evidence for this remarkable phenomenon comes primarily from observations of distant supernova, exploding stars that serve as cosmic yardsticks, their light appearing dimmer over time as they move away from us. These measurements consistently show a redshift in the light spectrum, indicating an expanding universe and, crucially, a faster expansion rate than was previously thought possible based on the combined effects of matter and energy. Dark energy is the name given to this mysterious force, responsible for accelerating that expansion. It's not a substance in the traditional sense. It doesn't clump together or interact with ordinary matter, but rather a property of space itself, an inherent tension pushing outwards against gravity's pull. The precise nature of dark energy remains one of the greatest unsolved mysteries in cosmology. There are several competing theories, each attempting to account for its observed effects. One prominent idea is that it represents a cosmological constant, a uniform energy density permeating all of space-time, proposed originally by Einstein, but later abandoned due to his own preference for a static universe. More recently, alternative models suggest dark energy might be a dynamic field, evolving over time, perhaps influenced by quantum fluctuations at the very beginning of the universe. These models introduce concepts like quintessence, a hypothetical fluid with negative pressure that drives acceleration, or modifications to Einstein's theory of general relativity itself, altering our understanding of gravity on cosmic scales, regardless of its precise origin. Dark energy constitutes approximately 70% of the total energy density of the universe, a staggering figure highlighting just how much we still don't know. Now, let's examine how this expansion affects the motion of galaxies within Laniakea. Imagine yourself as a single point within that vast network, drifting along with the flow. You'd notice that you're not simply moving directly toward another galaxy. Instead, you're carried along by a complex stream of galactic motions, dictated by the gravitational landscape of Laniakea. The galaxies nearest to the walls of the supercluster, those points where the expansion is most influenced by surrounding structures, are pulled inward, creating a kind of cosmic whirlpool effect. Galaxies further out, situated in the relatively flatter regions between these walls, are carried outwards with greater momentum, propelled deeper into Laniakea's expansive embrace. The key to understanding this movement lies in the concept of gravitational potential. Gravity doesn't just pull, it also pushes objects towards lower potential energy states. Galaxies within Laniakea occupy different potential wells, some higher than others, and it is their attempts to settle into these lowest energy configurations that dictate their relative motions. The expansion itself acts like a cosmic tide, constantly reshaping these potential wells and shifting the equilibrium of the entire network. It's important to note that this isn't simply about galaxies moving through space. Rather, they are being carried along by the very fabric of space-time as it expands. The distances between galaxies are not static. They are growing with time, stretching the universe out at an accelerating rate. Consider a simple analogy. Picture a group of people walking around a circle. Initially, their movements are relatively coordinated, but as someone pushes against another, creating a ripple effect, the entire group begins to move in a more complex pattern. Some individuals drawn closer together, while others are pushed further apart. Dark energy is akin to that initial push, an invisible force constantly disrupting the established patterns and driving galaxies towards ever greater distances. Within Laniakea, this expansion isn't uniform. It's strongest at the edges of the supercluster, where gravity's influence is weakest and gradually diminishes as you move toward the center. This creates an intricate mosaic of galactic streams, each reflecting the local conditions within that particular region of the network. The implications for our understanding of cosmology are profound. The discovery of dark energy and the accelerating expansion of the universe has fundamentally altered our picture of cosmic evolution. For decades, the prevailing model, the lambda CDM model, predicted a decelerating expansion driven by gravity. It painted a picture of a universe gradually winding down, with galaxies eventually drifting apart to infinity. Now we know that's not the case. Instead, the universe is in the midst of an accelerating phase, destined for a future where galaxies continue to recede from one another at ever-increasing speeds. This changes our perspective on the ultimate fate of the cosmos. No longer a slow decline into darkness, but a relentless expansion, potentially leading to a big rip scenario where the expansion becomes so extreme that it tears apart all matter, including atoms themselves. While this scenario is currently considered unlikely, it highlights the inherent uncertainties in our cosmological models and the importance of continued observation and theoretical development. Furthermore, Laniakea itself forces us to reconsider the very concept of scale in cosmology. We've long been accustomed to thinking about the universe as a collection of galaxies clustered together in relatively well-defined structures. But Laniakea demonstrates that our local cosmic neighborhood is just one small piece of a far grander puzzle. It's part of an even larger network, extending for 500 million light years and connected to countless other superclusters through gravitational threads. This interconnectedness suggests that the universe may be fundamentally more woven than we previously imagined, with every structure inextricably linked to every other component. The sheer scale presents endless questions about the distribution of matter, the formation of cosmic structures, and the ultimate fate of all things. The ongoing study of Laniakea through observations from telescopes like the James Webb Space Telescope and ground-based observatories offers a unique opportunity to test our cosmological models and refine our understanding of dark energy. By meticulously mapping the motions of galaxies within this network, scientists can probe the nature of dark energy with unprecedented precision. Each new measurement brings us closer to unraveling one of the universe's greatest mysteries, a mystery that is intimately tied to our own place within this extraordinary cosmic web. A gravity watershed defining our sprawling cosmic home. And as we continue to explore, observe, and analyze, it becomes increasingly clear that the expansion's echo, the relentless push outwards driven by dark energy, is not just shaping the universe's distant future, but is actively rewriting our present understanding of its entire history. And as we trace the contours of Laniakea, this expansive network of galaxies held together by the invisible threads of gravity, we begin to perceive that its very existence carries with it an extraordinary consequence, a subtle yet profound distortion in the fabric of space-time itself. It's a phenomenon so deeply interwoven with the workings of our universe that for centuries, brilliant minds wrestled with its implications, often obscured by the limitations of their instruments and theoretical frameworks. We speak now of gravitational time dilation, a concept initially conceived not as a scientific puzzle, but rather as an intellectual exercise in reconciling Newtonian physics with the startling predictions of Albert Einstein's theory of general relativity. The core idea is elegantly simple, yet profoundly unsettling. Gravity doesn't just pull things towards it. It warps the very geometry of space and time around it. Imagine space-time not as a rigid grid, but as a vast, flexible sheet, a trampoline, perhaps. And picture a massive object like our sun, or even a galaxy, as a heavy weight placed upon this sheet. The indentation created by that weight isn't merely spatial, it's also temporal, causing the fabric of time itself to curve and bend. The closer you are to such an immense gravitational source, the more pronounced this effect becomes. It's a consequence of Einstein's assertion that gravity isn't a force in the traditional sense, but rather a manifestation of mass and energy, warping the curvature of space-time, a curvature that dictates how objects move through it. Consider a clock placed near a black hole, or perhaps at the edge of our own galaxy within Laniakea. From an external vantage point, you would observe its ticking sluggishly compared to a clock far away in sparser gravitational surroundings. This isn't due to any malfunction of the clock itself, but rather a fundamental difference in the rate at which time passes relative to that external observer. The greater the gravitational field, the slower time flows for an object within it, relative to someone experiencing weaker gravity. It's a reciprocal relationship, too, from the perspective of the object deep within the gravitational well. It's the external clock that appears to be moving faster. This isn't something you would typically notice in your daily life, even near Earth. The time dilation is incredibly small, measurable only with extraordinarily precise instruments. However, it's a principle that has been repeatedly and rigorously confirmed through observation and experiment. Scientists utilize highly accurate atomic clocks, devices of unparalleled precision, aboard satellites like those in the Global Positioning System, or GPS. These satellites orbit Earth at significant distances, experiencing a slightly weaker gravitational field than we do on the surface. Without accounting for this time dilation effect, GPS would quickly become unusable, accumulating errors of several kilometers per day. The clocks on board the satellites tick faster than identical clocks on Earth due to their position in sparser gravitational surroundings. This small difference is constantly corrected by sophisticated algorithms, demonstrating a practical application of Einstein's theory and illustrating the tangible impact of gravitational time dilation in our everyday lives. These are not mere theoretical curiosities, but crucial components of technology that underpin much of modern navigation and communication. The data gathered from these satellite missions provide continuous measurements of this subtle time difference, offering invaluable insights into the nature of gravity itself. The meticulous tracking of these satellites, coupled with increasingly sophisticated models of space-time curvature, allows us to map the gravitational landscape of our universe with greater accuracy than ever before. But let's venture beyond the tangible and consider the theoretical implications, particularly as they pertain to interstellar travel, a dream that has captivated humanity for centuries. The prospect of traversing vast distances between stars presents daunting challenges, not just in terms of energy requirements or navigation, but also in understanding how time itself might be affected by extreme gravitational environments. As you accelerate towards a massive object, such as a black hole, or even across the immense gravitational gradients within Laniakea, the effects of time dilation become dramatically amplified. If you were to embark on a journey at a significant fraction of the speed of light, approaching the event horizon of a supermassive black hole, a point beyond which escape is impossible, time would pass for you much more slowly than it would for someone remaining behind on Earth. Imagine, hypothetically, traveling towards the center of our own Milky Way galaxy, within Laniakea's gravitational embrace. As you approach the galactic core, where the density of matter and energy are incredibly high, the time dilation effect would intensify to an astonishing degree, while approaching a black hole offers an extreme scenario. Even traversing the vast gravitational gradients within the network itself, navigating through regions of higher and lower mass concentration, would result in noticeable differences in the passage of time. For an observer on Earth, perhaps centuries or millennia could pass, while you experience only a fraction of that time within the denser regions of Laniakea. This isn't simply a matter of perception. It would fundamentally alter your biological processes, aging at a slower rate compared to those who remained outside this influence. Of course, such a journey remains firmly in the realm of theoretical speculation, bound by technological limitations we can scarcely comprehend today. The energy requirements alone for approaching relativistic speeds are staggering, and the intense gravitational forces would present formidable challenges to any spacecraft's structural integrity. However, contemplating these scenarios forces us to confront the fundamental nature of space-time, a reality where time isn't absolute, but is inextricably linked to gravity and motion. It underscores that the expansion of the universe itself, this relentless pushing outward driven by dark energy, is not just shaping the universe's distant future, but is actively rewriting our present understanding of its entire history. The very structure of Laniakea, this sprawling cosmic home, isn't merely a static arrangement of galaxies. It's a dynamic system, constantly influenced by gravitational time dilation, a subtle yet pervasive force that shapes not just space, but also the flow of time itself. As we continue to refine our observations and develop more sophisticated models, we move closer to unveiling the deeper secrets held within this gravity web. Secrets that may ultimately redefine our place in the cosmos and reveal new pathways for understanding the most fundamental laws governing reality. The beauty lies not just in the spectacle of these immense distances, but in the profound implications hidden within the simplest of physical principles. That time itself is a fluid, responding to the curvature of space around us. Here, within this immense web, our own Milky Way finds its place, nestled amongst countless others, all bound together by the invisible force of gravity. We are a small thread woven into an extraordinary tapestry, a cosmic address stretching across 500 million years and 500 million light years. Consider the scale of it, the sheer immensity of this network, and the quiet dance of galaxies moving towards each other, pulling apart, held in balance by the embrace of Laniakea. It's humbling to realize our own journey is simply one small step within this grand, unfolding story. Thank you for spending this time among the stars with me. If you enjoyed the journey, a gentle like and a subscribe help more quiet dreamers find their way here. Until next time, rest well and keep wondering about the cosmos. Good night.